topic for today is talking about the electric potential of single and multiple point charge particle. So therefore, in this topic, we want to know how much electric potential experienced at any point in the surrounding single charge or maybe a multiple charge particle. The requirement of this course is you should have the idea on calculating the amount of electric potential energy, because from there we will use that principle in order to derive the formula or calculate the electric potential at that point in the surrounding charge or charges. Okay, so suppose we have an stationary charge, let us say Q. It is a positively charged. We understand that because of this charge, it provides charge distribution, which is called as the field lines. And these are the electric field lines. And we understand that at different point, a distance from the center of this charge, it has a unique electric field, which means that this electric field varies with the radius from the stationary charge. Now, what's the effect of this charge distribution? The effect is if we have another charge, suppose Q naught being a moving charge, and call this as a positively charged. So, this charge will experience an electrostatic force because of the presence of the charge, and it is because of the electric field. The electric field are produced because of the charge distribution. So, since Q naught is placed on the region wherein there is a presence of electric field, then this charge experience a force. So therefore, that force, we understand it is related to the electric field. Also related with this stationary charge and that moving charge and its distance. So suppose you are asked how much is the energy produced because of this discharge. Then in our previous topic, we understand that calculating the amount of energy is multiplying the electric constant or the 1 over 4 pi permittivity multiplied by the product of the interacting charges, the stationary charge and the moving charge divided by the radius. So therefore, you have the unit of joules because this is energy. Another way to calculate the energy is if we have if we know the electric field at this point on this discharge, multiply it with the charge of the moving or Q naught and multiply it by the radius, then the answer is still the energy, which means that this will have a unit of joules also. Okay, so the question is, what is electric potential energy at this point or at any point from stationary charge? So therefore, if this charge produces electric field, then it has the ability to attract or to interact charge like Q naught. In other words, we can calculate the force in it, and we can provide the electric field. We can also provide the energy at that point. Then we can also calculate the amount of electric field at that point. But the question is, what is electric potential? Okay, so by definition, electric potential is at any point in an electric field has a potential energy per unit charge associated with the discharge at that point. So what does it mean? It's meant to say that the energy at that point divided by the unit charge, the result is electric potential, which means that by definition, the electric potential in symbol V, because if U is energy, big letter V in electricity, V means the electric potential. This is equivalent to the potential energy or U divided by this charge. So therefore, since we know already how much is the energy at that point, simply divide it by this discharge. So what will happen if you divide the energy by discharge? That result is electric field. How much is the answer? So therefore, this is the definition of, based on the statement, this is the definition of the electric potential. This is the energy per moving charge. So therefore, you have to substitute U here. So therefore, this is your U1 over 4 pi permittivity Q naught over R. This is the energy divided by the Q naught or the moving charge. This will be cancelled out. So what we have now is the potential, electric potential is equivalent to the 1 over 4 pi permittivity Q over R. So therefore, if you want to calculate the electric potential at this point, all you need to have in order to calculate is we need only the charge distribution, particle, and the distance away from the point of interest. So you have to divide it, Q over R, multiply the constant, that's it. That is the electric potential. Okay. Another way is we can utilize this because we substituted the U here with this value 1 over 4 pi permittivity Q naught over R. Now take note that we have another formula in calculating the U energy. So use this energy here, substitute it here, and divide it by the uh, moving charge Q naught. So therefore, this again will be cancelled out. So we have electric field times R. So therefore, another way to calculate the electric potential is to multiply the electric field at that point by R. So therefore, there are two formulas, and these formulas depends on the given. So you can use this formula provided that we have the charge and it's reduced. Meaning, if you want to know how much potential at any point, all you have to do is to identify the distance from the center, call it R. Then divide the charge by that R and multiply by the constant. The answer is the electric potential. Another way is you can use this formula if the electric field is known at that point. Then multiply it by the radius. Then the answer is the electric potential. Okay? So therefore, when you look at the formula, the electric potential, in order to calculate the value of the electric potential, we don't need the moving charge. So what we need is only the charge, stationary charge, and its radius. Unlike calculating the energy at this point, you need the two charges, the indirect charges, the source charge or the stationary charge and the moving charge. Then its distance. Okay? And notice also that therefore you cannot calculate the energy without the moving charge. But the potential, electric potential, does not require the magnitude of the moving charge. But we need this charge here. But it doesn't matter if we have no value, meaning we can bring anything. If we can bring any charge here, and the potential is the same. Okay? The same potential, any charge placed at this point, you will arrive the same potential because it will be cancelled out from the calculations. Unlike say, that of the energy, it requires the moving charge. Also with force. Force requires the interacting charges, but electric field does not. Okay? So the question is, okay, by the way, this electric field can be substituted here if the electric field, if that electric field, if the charge is a point charge. So if this is point charge, then this is the electric field. Recall in our previous video, there are many ways, or there are different electric fields for different charge. We have the point charge, this is the formula, and we have the line charge, we have the ring charge. So in this case, if we substitute the electric field here, you will arrive this one. Okay? Because when you substitute E here, this R will be cancelled, and this one will be reduced to 1. So therefore, leaving 1 over 4 by permittivity Q over R. So therefore, these two formulas are the same. Okay? Depending on the given. So, take note that electric potential is a scalar quantity. So, same as energy, because energy is scalar, then electric potential is also a scalar quantity, which means that no directions. Okay? There is no involvement of I hat, j hat, and k hat for the direction along x, along y, and z. Okay? Why? Because this is scalar. But take note, we have the energy positive, and we have the energy negative, and we have energy zero, which means that the electric potential also, it can be positive, it can be negative, or it can be zero. Okay? So the question is, when can an electric potential be a positive? The answer is, look at the formula. If the charge is positive, then the electric potential is positive, which means that if the charge dominates the positive value, then this is positive. If this is negative, this is also negative. Okay, so no problem with regards to positive and negative. What about zero? How can we say that the potential is zero? Okay, now take note the charge is always present. The only way that the electric potential becomes zero is to have the greatest or maximum or an infinite value of R. So if you have a very long or very far distance, in a far distance away from that point, away from the charge, the potential is zero. Okay? Now the next question is, what is the unit? If the unit of U is joule because it is energy, the unit of force is Newton, electric field is Newton per meter. Now what is the unit of the electric potential? Okay? The unit can be obtained using the definition. Look at the definition. The definition of electric potential is U over Q naught. The unit of Q is joule, and the unit of Q naught is coulomb. So therefore, the unit should be joules per coulomb. Okay? So therefore, take note that joules per coulomb is volt. So therefore, the unit of electric potential is volts. Okay? So 1 volt is, or 1B, big letter B, is equivalent to 1 joule per coulomb, because this is coming from the definition. Now, when you examine also clearly this formula, this will arrive joules per coulomb. So therefore, this will be a unit of volt. Also this one, if you analyze clearly within the unit, you will arrive the unit of joules per coulomb, and it is volt, because for every joules per coulomb, it is equivalent to 1 volt, vice versa. Okay? So, okay, how will you compute? Okay, going back to the problem, what is the electric potential at this point? What are the requirements? The requirements are, you need the magnitude of this, you need the amount of the charge, and you need R. That's it. Divide that by this one, then multiply it by the charge, then the result is the electric potential. Or, by definition, this is U over Q naught. If you know U, then substitute it. Okay, then this will be cancelled out. Then you come up with 1 over 4 pi permittivity Q over R. Okay, so this is how to compute the electric potential. Since this is positive, this is also positive. If it is negative, then this will become negative. Now, if the point is closer to R, it has a greater value. Okay. Now, if it is far away from this point, this is approximately 0. Okay? Not necessarily be 0, but approximately equal to 0. In mathematics, approximately equal to 0 is very close to 0. So we can ignore it. Now, what do you think? What is the maximum? What is the maximum potential? What is the maximum potential that this charge produce? what is R. Okay, take note that if we are moving closer to the charge, it will increase its magnitude. So if you want the maximum, it should be in the at the surface of the charge. Okay, at the surface of the charge, because this R is center to center, so therefore the maximum R that this charge can provide a maximum potential, that distance should be the radius of the sphere or the particle. Okay. Now, what do you think? What is the electric potential inside? Now, take note that the charge is only at the surface. Okay. So if you are to calculate the amount of electric potential inside, the answer is the same as the electric potential at the surface. Which means that if this is 150 volts, the potential inside is also a 150 volts. Now, if you remember in our previous topic on the uh, Gauss law, application of Gauss law, we solve problems of a particle. So, if you are asked how much is the uh, flux inside the sphere, then the answer is zero. Why? Because there is no charge, enclosed charge. Okay? So if there is no flux, therefore there is no electric field. So therefore, the answer is, what is the electric field inside? The answer is zero. The reason is, there is no charge inside. But for the electric potential inside is the same as the electric potential at the surface of the R. So therefore, the minimum R that can be used to calculate this formula, the electric potential, is only at the radius of the sphere. Okay, so that's very clear. Okay, now what will happen if we have the multiple charges surrounds up to this charge? We call this as the electric potential of a multiple charge. What will be our formula to calculate the electric potential at this point, whose radius from charge 1 is R1 and charge 2 is R2, charge is R3? What will be our electric potential on this moving charge from the 3 or more stationary charges? Okay, so to answer is, recall the electric potential energy for a multiple charge. If in the multiple charge, in calculating the energy, there are two energies that formulas can be used: energy from a single charge and energy from a multiple charge. And this is a multiple charge. Okay, so take note that the electric potential is what? By formula, it is U over Q. So if this energy is the energy at that point, because these are the surrounding charges, because the formula says calculating the energy is the moving charge divided by the 4 pi permittivity, or the electric constant multiplied by Q naught, okay, the same or not, is equivalent to the sum, the product of the sum of the charge per R. So meaning Q1 over R1 plus Q2 over R2 plus Q3 over R3. Now take note, this is algebraically calculated, so you have to consider the sign. Okay, so consider the sign, then you come up with an answer. Multiply this with this value, then the answer is energy. So therefore, we can calculate the energy at this point. So if we can calculate energy at this point, we can also calculate the electric potential at that point also, because electric potential is U over Q naught. So you have to replace it here. Then take note that we can cancel the Q naught. So therefore, if you divide this one, the result is 1 over 4 pi permittivity quantity, the sum of the ratios of charge per distance, Q1, R1 plus Q2, R2. So the difference between the two, the energy requires the charge, but the electric field does not require the moving charge. So therefore, the only difference of these two equations is the presence of the Q naught. There is Q naught and the energy, there is no presence of the electric potential. Okay, so this is the formula in calculating the electric potential of a multiple charge particle. Okay, so therefore, look at this one. Suppose we have the surrounding charges and you are asked how much is the electric potential at that point. So all you need to do is what? Look at the formula. A while ago, this is R1, R2, R3. So therefore, all you need to do is 1 over, because this will be removed. So 1 over 4 pi permittivity. This is Q1 over R1, Q2 over R2, Q3 over R3. Combine it algebraically, then multiply the Q over 1 over 4 pi permittivity. Then the answer is the potential. Okay? So very simple calculations if we know the formula and if we know the charge and its distance away from that point. Okay. So therefore, the electric potential of a multiple charge particle is, this is the power series uh, notation. Okay. So this one is the same as this one. Okay. Why? This 1 over 4 pi permittivity, okay, as is, and this one, take note, this is, you are asked to sum up. So asking for sum up is, in mathematics you can use the sigma symbol, means sum. Okay, and this lower limit is I, so I starts from 1. This is an integer, start from 1, then it will move to 2, 3. Okay, so summing up all Qi's over Ri's, starting from I is equal to 1. Okay? So therefore, when I is equal to 1, substitute here becomes Q1 over R1. Okay? Then next round, this will becomes I2. So this will be Q2 over R2, this one, Q3 over R3, and so on, and so on. Okay? So therefore, this is the ideal way in presenting the multiple charge particle. Why? Because if you use this one, and there are 100 charges, okay, 100 charges, and you need to know how much is the point, potential of that point, and you have to provide it the solution or the formula. How will you present it? So it is not advisable to use this one. You have to use the power series notation. Okay, although the two are the same, but this one is actually the usual presentation of the electric potential for a multiple charge particle. Okay? So in order to understand, we have to solve application problem again. So look at the problem. The problem says that we have an electric dipole. These are the dipole. Why? Because this charge is the same as charge. This is plus and this is minus. And they are separated by a distance. Now in this case, we have 12 nanocoulomb positive interacted with a negative 12 nanocoulomb, and the space between is 10 centimeters. Okay? 10 centimeters. Okay. Now, the question is, compute the electric potential at points. What are the points? Point A, point B, point C. Okay, so we will provide three answers. Potential at A, potential at B, and potential at C. Now, look at the variation of the electric potentials. Look at the result. Okay? So, how will you answer this problem? To answer is, use there are two formulas, diba? Look at this one. We have electric potential of the single charge, this one. Okay? Now, we have the electric potential of multiple charge. Okay. Now, in question number 1, you are asked to calculate how much is the potential at point A. Now, take note, point A is 6 centimeters away from charge 1, while point A is 4 centimeters away from charge 2, and they are the point is in line with the line that connects the two charges. Okay, so the point here experience an electric potential of the two charges, so therefore we use the multiple charge. So use this one. Okay, so therefore what is important is you have to know what is R. So therefore use the formula. This is the answer. This is a formula to be used. The electric potential at point A is the electric constant multiplied by Q1. Where's Q1? Q1 is 12. Is to R1. Now, question, where is R1? And what is the definition of R1? What is R1 here? Take note, R1 is the distance or the position from the source charge towards the point of interest. The point of interest is A. So therefore, R1 should be measured coming from positive towards the charge towards the point of interest A. So call this as R1. Why R1? Because this is the distance from charge 1. Okay, so this will be our replace. Now in this case, R1 is 6 centimeters because this 6 centimeters is from center to center. And R should be start from the center of the charge towards the point of interest. Okay, now where is R2? R2 is the position of charge 2, okay, towards the point of interest. So meaning, start from charge 2 towards the point of interest, that will be our R2. So the R2 is 4 centimeters. So we will substitute here the R1 to be 6 cm, R2 to be 4 cm. And this one is Q1 and this should be Q2. Take note, negative. So you have to use negative algebraically. So then, 1 over 4 pi permittivity, it is electric constant. So therefore, substitute. The electric constant is 9 times 10 raised to 9. What's the unit? This is Newton meter square per coulomb square. Okay. Now this one is the charge. Okay. We multiply it by times 10 raised to negative 9. Okay. Because we want to convert the 12 nanocoulomb to a coulomb. So again, converting the nano is to multiply 10 raised to negative 9. So that it will be consistent with our constant. The unit should be put in place in SI. Okay, so that the resulting unit becomes volt. Okay, you cannot provide a unit of volt if the unit is inconsistent. Okay, so then 6 is the 6 centimeters. Now take note that in 1 centimeter there are 10 raised to negative 2. Just like 1 nanocoulomb, in 1 nanocoulomb there are 10 raised to negative 9. So therefore, you just multiply the 10 raised to 2 here for 6 in order to convert the centimeter to meter. So therefore, do it the same. Then calculate. And the answer is negative. Okay, negative 900 volts. Okay, why negative? Look at the point. As I've said, the electric potential can be negative, can be positive, or can be zero. So, what is the reason of having zero? For a multiple? Okay, for a multiple, because your A is closer to the charge, negative. It provides a greater, which means that this term is a negative. Okay, greater negative compared to a smaller value of the positive. Okay, so therefore this will provide negative 900. So which means that if the point is close to negative, the potential becomes negative. Okay, now what do you think if you change this position of A, instead of having 4, say it 2 centimeter? What do you think? What will be the result here? Surely, this will increase negatively. Okay? So, if you continue moving towards a place at the surface of that charge, then it provides a greater negative charge, negative potential of the interaction of the two charges. So, therefore, if you want to know where should be the point wherein the negative potential is negative is maximum, then say it at the surface of the charge. Okay. Now, proceed to letter B. Letter B is you are asked to solve for the potential at B. This one. Okay. So, again, use the same formula. 1 over 4 pi permittivity, Q1, R1. But this time, your R1 now is different. Okay. If you remember, in calculating at point A, our R1 is coming from the positive towards A. Now, in this case, we change our position here. So, all R should be directed toward this point. So, therefore, if you want to ask, where is R1 of Q1? The answer is coming from the center towards this point. This is your R1, which means it is 4 cm. Previously, this is 6, and the direction is towards. So, this is going to the point, positive 6. This one, from this point going to this point is 4 centimeters. Okay? Now, where's your R2? R2 is the distance of the charge 2 towards the point of interest. So, where is it? It is coming from the center of the charge, moving straight towards the B. So, therefore, this is the R2. So, substituting the formula here, take note that the constant, the same charge one is the same, charge one is the same as this. The only difference is R1 and R2. In this case, our B is 4 centimeter, R1 at point B is 4 cm. Our R2 is what? This is 4 plus 6 plus 4. Total of 14 centimeters. So therefore, substitute everything the same except this one. Again, this is your R1, which is 4 cm times 10 resolutive 2 to convert to meter. R2 is 14 multiplied by 10 resolutive 2 to convert to meter. Then the same, the upper part. Then calculate. Use a calculator. The answer is 1,930 volts. Take note. Positive. So why positive again? Because the point is close to the positive value. Take note, they have the same magnitude. So therefore, if you are closer to here, you will have experienced a positive electric potential. Okay. Finally, what is the electric potential at point C, where C have equidistance from charge 1 and charge 2. Charge 1 is positive 12, charge 2 is negative 12. So what will be the potential at point C? So use the formula again. It is 1 over 4 pi permittivity Q1 because we are using charge 1, Q2 because our charge 2. Then we have now another value of R1 and R2. Okay, what's R1? R1 again is coming from the charge going to the point of interest. So you have to connect a line towards the point of interest. This is R1. And here, this one also, at this point towards the point is R2. So take note, 13, 13. So R1 is 13, R2 is 13. So substitute again, same charges, different in R. So this is 13 times 10 raised to negative 2, 13 times 10 raised to negative 2. Okay, take note that they have the same, di ba? This value is exactly the same this. And this is positive while this one is negative. So without calculations, the result is what? 0. Why? Because this term is the same as that. And this is negative and this is positive. So therefore, this will be subtracted. Okay? So this is 0 volts. Okay, so therefore, we already understand how to calculate the electric potential at any point. And we have two formulas. The electric potential at single charge and the electric potential in a multiple charge particle. That's all. Thank you. The next video is talking about the electric potential difference.